Hi everyone. In this lecture we are going to talk about metallothioneins, transferrins, and specifically we're going to be looking at metal transferrin storage in the body. So, to start this off, I want us to recall what the human body is made of by elements. We have natural elements, we have elements that don't even exist in our body, but let's look at the ones that are in our body. Now, recall from your intro biology class in high school, or if you've had any biology, which I hope you have if you're chemistry, you've probably heard of this mnemonic before, the Chomps mnemonic. You might even see it with an S. Okay, we'll get to that in a little bit. This is going to make up roughly about like 95% of your body mass, is these simple 6 elements, okay? A very, very high amount. And it's used in the organic molecules you'll see. For example, cysteine residues, which we'll see later, in sulfur, right? That's the R group for cysteine. Phosphorus, you'll see this in adenosine triphosphate, ADP, AMP, those important, not they're signaling molecules, but also they're the source of energy in the body. And of course, carbon, hydrogen, oxygen, nitrogen, because, well, that's makes up organic molecules. I mean, for crying out loud, you had 2 semesters of organic chemistry. You should know that these are making up most of the molecules of life. Now, we have other elements and we'll classify these. Let's say these are the most abundant, right? So this is the first class I'm going to talk about. The second class I want to identify are the electrolytes, so things used in your cells as concentration gradients or ligands of signaling molecules in your enzymes. Now that's going to be things like sodium, calcium, 2+ maybe could be one. You'll even see anions like chlorine, trying to think of another one, potassium, right? And if you recall, those pumps that you've seen, like the potassium, I think it's the potassium sodium pump. I'm probably getting that mixed up. But that's very important. It's used in life to signal things. Okay? You might even see magnesium in there, but we're not going to classify magnesium as an electrolyte here. What you'll also see are the important protein folding metals, the D block metals, okay? So let's shift into there. Well, that would be talking about things like iron, both 2+ and 3+. This is especially helpful in mammal species with the use of blood or carrying oxygen to the mitochondria through the bloodstream. That's where iron's coming from. This is our third class of metals. So this was our second, it's our third. You'll also see things like zinc, 2+, or vanadium, and its oxidized forms. They're all important to life and they all play a critical role. But for this lecture, we're not going to really talk about these guys so much. We're going to talk about the iron because by abundance, there's a couple thousand milligrams of that in your body at any given time, where this is only a few milligrams. So big emphasis on the iron in mammals, which, you know, we're mammals, so that's kind of important. The third class is elements that are natural, so they occur in nature, but the body does not want. You could think, in this case, like maybe copper or mercury. Or you don't want a lot of it. Maybe you use it in some weird side reaction, but really, like mercury, you're not going to really want in your body, no matter what, okay? So, what I want to look at today, and the course of this lecture, is we're going to look at the iron. We're also going to look at the heavy metals. That's going to be the focus of this lecture. So without further ado, let's just hop right into it. We'll start with iron. Now, if you can recall the use of iron in living mammals, well, you know blood, and you know that blood is going to carry oxygen through hemoglobin, and the main binding, the thing that brings all the hemoglobin components together is iron. Well, how do we get iron, 1, and 2, how is it transformed in the body? Where is it stored? Well, that's what we're going to go over here. Now, The general system is that the iron is ingested by food, of course, and it reaches your stomach where something called a ferroxidase is going to turn the iron 2 plus into iron 3 plus. It's then going to absorb into your bloodstream and it will get stored in the liver. Now, what we're going to find is that the liver is a humongous storage of these metal ions that we need. It's the warehouse that holds all of these essential metals that we need. Iron's one of them. Now, the question remains, how does it get from the stomach to the liver? Does it just move there? Does it just wake up one day and decide, I'm going to walk over here and make my way over to the liver? Well, the answer is no. It does something. It does this through the bloodstream by a specific enzyme. It's a big focus of this chapter, and it's going to be the idea of the transferrin. Trans meaning transfer, ferrin meaning containing iron. Or sorry, to transfer iron, I should say. And it looks something like this. Now, there's 2 units of these, and it's about 80,000 Daltons in molecular weight per 1 transferrin. So for every 1 transferrin, you can carry 2 irons. Now, what does this look like? Well, here you have an asparagine residue, which is in coordination with the iron. You also have a histidine residue, which is in coordination with the nitrogen lone pairs here. You also have 2 tyrosine molecules, and they're deprotonated phenols that are in coordination. There's 2 of them in coordination with the iron. But also, this residue here is really cool. It's not arginine, which is directly bound to the iron. It's specifically this carbonate ion. And we'll get to that in a little bit, but it's a bidentate ligand to that iron. And what this does is it allows that iron to be held tightly in that enzyme where it goes from the stomach to the liver. You can think of this as like a transport protein. It's going to transport the iron from the stomach to the liver. And the specific biology we're not going to get into because this is chemistry. Get on my level, biologists. But anywho, let's talk about the carbonic acid bit, because I think it's interesting. If you remember in the blood is filled with carbonic acid. It's the buffer of blood. It resists pH changes at about 7.4 pH. Now that system looks like this. You have the carbonic acid, H2CO3, which can be deprotonated into bicarbonate, HCO3-, which can also go to CO3, and that's going to be 2-, okay? So this system usually hangs out in this neighborhood. So we can imagine there's a lot of free CO3 2- available. I believe this is like a cofactor or coenzyme, one of the two. And it's an example of why acidifying blood is just a terrible idea. Because when you acidify blood, you're going to shift the equilibrium back this way. You're going to get a lot of carbonic acid, and that's going to disallow the mechanism for transferrin to deliver iron to make hemoglobin. So I think it's important to just kind of see how all this interplays with your life. This is one of them. Okay, so let's talk about cysteine. Now, if you remember what the cysteine amino acid residue looks like, you remember that it has a thiol. It goes one carbon out, and then it connects to the rest of the amino acids. So we just get the generic amino acid structure like that. So here's the R group. And these things that we're going to talk about for transporting metals out of the body is known as metallothioneins. So kind of a big word, but what they are these big webs of cysteine residues put together in about 500 Dalton to 18,000 Daltons. So these humongous webs of cysteine is going to encapsulate, which we'll find, these heavy bad metals for our body. Now, you might ask, well, what does this even look like? Well, you have, I'm gonna discard drawing the rest of the cysteine residue. But whenever you see SR, that's going to indicate the cysteine and the rest of the residue. So let's take, for example, copper. Copper, it's going to form these tetradentate webs of cysteine residues like this. And in fact, even here, it can branch out like this, and you're going to see these humongous webs grow. And I'm going to stop here, but these webs can get 500 to 18,000 daltons long. So these are like scavengers. You can think they just are going to find a metal that it doesn't like, usually a soft metal, because these are soft ligands, of course. So like things like mercury 2+, very soft. Copper plus, that's a soft metal. It's going to find them and rip them out of whatever medium or matrix it so pleases. But that's all I really had to talk about today. That was what was covered in the book chapter that I was assigned. Really cool stuff in this chapter. I encourage you to read the chapter to get an even more thorough understanding of this. But remember, transferrins, metallothioneins, that is the whole topic of this chapter, really, specifically relating to metal storage and metal transfer or transportation. So